Previously, we have classified quadratic spaces over finite field. Coming up next, we are gonna classify regular quadratic spaces over p-adic numbers. Now the difference is that for finite fields, quadratic spaces are gonna be completely classified by two invariants, dimension and discriminant. For quadratic spaces over QP, we need to add one more invariant, the Hasse symbol. So now we're gonna define the Hasse symbol. To that end, we need to first define the Hilbert symbol. So this Hilbert symbol, check whether or not the conic ax squared plus by squared minus 1 has a root in K. If the underlying field K is a FP, is a finite field, we usually would write ABP like this. But I will often just skip it when we know the underlying field. This is a generalization of the Legendre symbol. Now the Hasse symbol is just a product of Hilbert symbol, but the definition of the Hasse symbol here seems to depend on an orthogonal basis, because this splitting of V is with respect to an orthogonal basis. So we need to show that it's well defined and it's actually independent of the choice of the orthogonal basis. Let's start by looking at the case when the dimension of V is equal to 2. i.e. in that case V is just A1, A2, and the Hasse symbol is just the Hilbert symbol applied to A1, A2. So the Hasse symbol can be either -1 or 1, and it's 1 exactly when the Hilbert symbol is 1, that is when this quadratic has a solution. But this is equivalent to saying that 1 is represented by V, and whether or not 1 is representable in V by the quadratic form in V is independent of the choice of the orthogonal basis. So we see that in the case when n is equal to 2, the definition of the Hasse symbol is independent of the choice of the orthogonal basis. Now we want to prove that the Hasse symbol is well defined for the case when V is of dimension greater than or equal to 3. So we look at two different orthogonal bases of V and look at the corresponding splitting of V. We want to show that the Hasse symbol defined with respect to the AI is going to be the same as the Hasse symbol defined with respect to the BI. To this end, we want to use the width chain equivalent to be able to assume that V3 is equal to W3, V4 is equal to W4, and so on. So Vi is equal to Wi for all I greater than or equal to 3. That is why we separated out the case when n is greater than or equal to 3. Well, so what does width chain equivalent theorem say? Well, if we have a quadratic space, a regular quadratic space V, as we do have now, then let's say we have two orthogonal bases, B and B prime. The claim is that we will have a finite chain of orthogonal bases starting from B and ending at B prime, such that if we look at any two consecutive bases in this chain, then Bi is gonna be obtained from Bi minus 1 by changing at most two elements. So they differ by at most two elements. Now how is this related to our proof? Well, suppose that we can show that the Hasse symbol defined with respect to one basis doesn't change when we change the basis by just two elements, and that means that for any two consecutive bases in a chain, the Hasse symbol defined with respect to one of them is the same as the Hasse symbol defined with respect to the other one. But then that means that for all the bases in a chain, the Hasse symbol defined with respect to all of them are going to be the same. And because any two orthogonal bases are going to be connected via such a chain, this means that the Hasse symbol defined with respect to any orthogonal bases are going to be the same. So here, without loss of generality, we can assume the bases Vi and Wi are consecutive in a chain. That means they differ by at most two elements. That's why we'll assume that V3 is equal to W3, V4 is equal to W4, and so on. Vn is equal to Wn. Observe that then Bi has to be equal to Wi for I greater than or equal to 3, because Bi is just Q of Wi, right? And so that's going to be equal to Q of Vi for I greater than or equal to 3. So thus we have the following isometry between these spaces. These are both isometric to V. Now by width cancellation, we get that this space is isometric to this space. So by the previous case, the case when n is equal to 2, we know that the Hasse symbol and which equals to the Hilbert symbol in this case are going to be equal. So now we're ready to show that the Hasse symbol defined with respect to the AI is equal to the Hasse symbol defined with respect to the BI. So the Hasse symbol defined with respect to the AI is given as follow, right? So we can separate out the factor that is A1, A2, and then separate out other factors that contains A1 and A2. Now this is B1, B2 by the discussion above. This we can combine by property of the Hilbert symbol. And here this part we don't have to worry about because we know that for I greater than 2, AI is equal to BI. So this is really just BI, BJ. Now this AJ here is just BJ because J is greater than 2. So the last thing we need to convert into the BIs is the A1, A2. Now remember these two spaces are isometric, right? So they must have the same discriminant. But their discriminant is just the product of the AIs or also product of the BI, so these must agree up to a square. But when this term is changed by a square, the Hilbert symbol doesn't change. So that means that this symbol is equal to B1, B2, Bj, which is equal to B1, Bj times with B2, Bj. Now look, all of these are just factors of the Hasse symbol defined with respect to BI. So we have proven that the Hasse symbol is well defined independent of the choice of the orthogonal basis of V.